Hello everyone. In this video, I would like to work through a set of exercises which will reinforce our study on the concepts of sets and subsets. We will begin with the exercises which are about expressing sets. Now we learned that there are three ways to express sets. One is the description way. That means we just describe the set in words, which can be a little bit long-winding and as well as tedious. Normally in mathematics, we like to represent things as symbols or with notations, right? The other way of expressing sets is by the roster method, all right? So in the roster method, we use a convention by which we list all the elements of the set within braces. So what we see here are sets expressed in roster method, all right, like B equals, and then we use the curly brackets, parenthesis, and then we list all the elements in the set, all right? And the other method is the set builder notation. Set builder notation, which is a more concise way of expressing a set, all right? So the first question says, express each set in set builder notation. So all these sets that we have to express in set builder notation are currently in the roster method, all right? So in the roster method, we start with a letter and then equals, and then within curly brackets, we list all the elements of the set. And the letter on the left-hand side, like B equals, is the name of the set. We also give a name to different sets. So this particular set containing of values between 7 through 14 is named as set B. All right. So with that, let's try to change or express the roster form into the set builder notation one by one of the different sets given here. Now, before we jump into working on these specific examples, let's go over the general form of the set builder notation, all right? So in the set builder notation, we start with the name of the set. So if the name of the set is A, then we write the name A or B or C as the case may be, and then an equal sign, but this equal sign actually interprets as is. So A is, and then we open a curly bracket, and then within the curly bracket we write a lowercase x, which represents the different elements in the set. So x followed by a vertical bar which reads as such that. So x such that, and then a condition, all right? And then we put in a condition that meets the different elements of the set. So the conditions will come from the property of the elements in the set, all right? And it can be more than one condition. So in that case, we will connect the conditions using the AND statement, all right? So with this general form of the notation, we'll go into rewriting each of these sets which are currently in the roster form, converted to the set builder form. So going to the first set given to us in roster form is B equals or B is, and then we have within the curly brackets a list of numbers which are the elements of set B. So we have to convert this and rewrite it in set notation using the set notation, all right? But before that, let's study the elements. We see over here the elements are all numbers and they are all natural numbers. Recall that natural numbers are counting numbers starting from 1, They are all integer values. They're counting numbers. They are all positive integer values. But this particular set starts from 7 and has values up to 14. So we have to state that in our set notation as well, or as one of the conditions. All right. So the way we are going to start this, writing this in set notation, is b equals. All right. So in set notation, this is going to be b and then equals, which is to be read as is. So b is, and then this curly bracket. So let's open the curly bracket, and then x, and then such that this vertical bar is to be read as such that, and then the first condition is that they are elements from a set of natural numbers. All right. So how do we write that? So x such that x belongs. So this is the notation to represent belongs. All right. Belongs or is a member of. Let me write that here. This notation means is member of, or is member of, or we can also say is an element, is an element of. All right. So x belongs to the set of natural numbers, and we indicate natural numbers with a capital N. So x belongs to the set of natural numbers. However, it's not all natural numbers. It's numbers starting from 7 all the way to 14. So how do we write that? So you have to use your AND condition. So AND x is a value between 7 and 14 inclusive. So you write it like this: 7 less or equal to x, and then x is less or equal to 14. All right. So that is the complete set notation of set B in roster form, containing elements of 7, 8, 9, 10, 11, 12, 13, 14. All right. So this was the first example. Now the next one is A equals, and then the number is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is going to work the same way. These are again natural numbers, starts from 1 to 9. So you're going to write it as A is. So this time the name of the set is A. So A equals, which reads as A is, open your curly brackets, then X, then the vertical bar, which means X such that X belongs to the set of natural numbers and its only value starting from 1 to 9 inclusive. So and 1 less or equal to x less or equal to 9, and close your curly brackets. All right. Let's look at the next two examples, which we will see that they are of a similar type. Over here it says C is, or C equals, and then in the roster form we have the elements listed: 3, 6, 9, 12, and then the 12 is followed by 3 dots, which means ellipsis. All right. And an ellipsis tells us that the pattern continues on and on after 12. All right. So let's study the pattern, because that we will have to use or describe that pattern in the set notation. So 3, 6, 9, 12, these are again natural numbers as we see. However, there's one more pattern that we must identify. We see that each of these numbers are multiples of 3. So 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, then 3 times 4 is 12. So they are increasing in multiples of 3. So the way we describe it is C, again start with the name of the set, C equals, and then open parenthesis, open curly brackets, X, such that the vertical bar, X is a member of the set of natural numbers and X is a multiple of 3, is a multiple of 3. And close your curly brackets, and that completes the set notation of set C. All right, look at the next one. You'll see that it follows a similar pattern, but it's a different multiple. Again, the set consists of elements which are natural numbers. We have the ellipses, and then the elements, individual elements, are multiples of 5. So 5 times 1 is 5. That's the first element. 5 times 2, 10. 5 times 3, 15. 5 times 4, 20. And the process continues. The next set of numbers will follow the same pattern. So we'll write it as D equals, open brackets, X such that X is a member or belongs to the set of natural numbers, and denotes the natural set, the set of natural numbers, and X is a multiple of 5. All right, of 5. All right, so the next one is E is the set of odd natural numbers. Again, follow the same notation, E equals or E is, and then open curly bracket, X such that X is a member of the set of natural numbers. So X and then the symbol for belongs to, and then N for natural numbers. And what's the next condition? That they are all odd numbers. So, and X is an odd value, odd number or odd value. All right. What about the next set? It says C is the set of months that contain less than 30 days. So it's going to be a set of months, but the condition is that the month has to have less than 30 days. That's important. All right, important condition. So we are going to write it, start it the same way, C equals, and then open your curly bracket, X such that, that vertical bar for such that X is, what is a month that has less than 30 days? There's only one month in the calendar which has less than 30 days, and that's February. So just write X is February, right? Let's go on to the next one. It says F equals, and then within brackets we have numbers starting from 15 and then goes all the way to 100. Now, because there is a lot of elements in this, instead of writing all the numbers, we just put an ellipsis and then write the terminal number, the last number at the end. All right. If we do not have the last number at the end, then that means it's an infinite set. However, here we start from 15, 16, 17. So we do represent 3 numbers, and then this gives an idea of the pattern in which the rest of the elements would progress, but the last element in the set is 100. But to write it in set notation, it's the same as what we used before. You start with F equals. So name of the set is F, followed by an equals, which reads is, and then open brackets, X such that X belongs to the set of natural numbers. All of these are natural numbers, as we see, counting numbers. But the other condition is and 15 is the lowest value and is inclusive. So 15 less or equal to X, less or equal to 100. All right. Now the next set of questions is about looking at each of these sets given below and determining whether the statements are true or false. Right? So we'll start with the first one. It says over here, E, surrounded by curly brackets, is a member or belongs to the set containing A, E, I, O, U. All right. Now, E is an element in the set. However, the way it is, the E on the left-hand side is expressed is not as an element, but as a set by itself, right? So on one side, on the left-hand side, the E is really a set and not an element. Whereas on the other side, this A, E, I, O, U is a set. All right, so the answer to this question is really, it's false. It's a false statement. Why is it false? Because over here, the set E, it's trying to say set E is a member of the set containing elements A, E, I, O, U. All right. If the individual elements were sets, then this would have been true. All right. However, we have a set cannot be a part of another set which only contains elements. We can have a set with sets as elements, that's fine. However, in this statement, these A, E, I, O, U are not sets, but they are just individual elements. So this is false. So we have to give a reason that E surrounded by brackets is a set, whereas A, E, I, O, U, A, E, I, O, U are a set of elements, All right, so that is the reason this is false. In order for this to be true, we would have to write it like this: E without the curly brackets and then the belong to symbol, and then followed by the set A, E, I, O, U. All right, this is a true statement, but we have surrounded the E with the set braces. Therefore, that's what makes it a false statement. Now, the next set of questions is to go through the statement and determine whether the statements are true or false, and we will also give an explanation why it's true or why it's false. All right. So the first statement says E surrounded by curly brackets belongs to the set A, E, I, O, U. All right. Now, the problem with this statement, first of all, is false. So let me explain why it is false. It's because when E is surrounded by brackets, this is not an element, but it is a set. All right. Because E is surrounded by the curly brackets, it's a set. Whereas this set on the right-hand side is a set of individual elements. All right. Therefore, you cannot have a set be a member of a set which has individual elements. Correct? So that is the reason this should be marked as false. All right? That's why it is a false statement. If we have the E without the curly brackets, if it was written as E belongs to A, E, I, O, U, then this would have been a correct statement. In that case, this would have been a true statement. However, since E is surrounded by curly brackets, that means E is not just an element, it is a set. And on the other side, we have a set of elements. Therefore, it is false. So the way we can write the explanation is false because E, all right, E surrounded by brackets is a set, all right, which is not a member of the set A, E, I, O, U, all right, made of individual elements or consisting of individual elements. All right. So we have to compare apples to apples. So we cannot look at a set and say that or determine that it belongs to a set of elements, a set containing individual elements. All right. The next statement says B is a member of the set A, B, C, D, E, F. This is a correct statement because over here the B is without the braces. That makes it an individual element. And yes, there's a B within the set A, B, C, D, E, F. Therefore, this is a true statement. All right, this is true. All right, however, if this B were to be surrounded by curly brackets, then it would have been false. All right, so keep that in mind, that when you're comparing or trying to determine if an element is a member of a set, then it shouldn't be surrounded by curly brackets. The next one is H belonging to A, B, C, D, E, F. This is a false statement. Why? Because within the set, there is no element which is H, correct? Therefore, this is a false statement. Why? Again, the explanation is there is no H in the set. All right, in the set listed. All right, so the next one says February belongs to the set months of the year. Again, this symbol can be read as belongs or is a member of. So February is a member of the set of months of the year, which is true, correct? The February is a month of the year. So this is true, and it's pretty obvious. The next one says 3 does not belong. So to indicate that something is not a member of or does not belong to a set, you write your belong symbol and then cross it out with a diagonal. All right. So 3 does not belong to the set. Now note that this set given here is in the set notation form. So X such that X is a member of natural numbers, is a member of the set of natural numbers, and X is odd. All right, so again, read carefully the statement. It says 3 is not. So let me write it down over here. What this is saying is 3 is not, because that symbol is crossed out, we should read it as 3 is not a member. All right, and the set that we are considering, that we are comparing or we are looking into, is the set of natural numbers where all the elements are odd values. 3 is a natural number and it is an odd value, so it should belong to this set, correct? Therefore, this is a false statement. We should mark it as a false statement, and again, to explain, you have to say that because 3 is a natural number, and is odd, it should belong, or it does belong, to the set. All right, to the set. So that's a false statement. The next one says Tokyo is a member of the cities in the United States. Again, this is again false because Tokyo is a city in a different country. United States is a country, and Tokyo is not one of the cities in United States. So this is false. All right, again, always back it up with an explanation. Tokyo is not a city in the United States, in the US. So this is a false statement. The next one says 9 is a member of or belongs to the set 1, 3, 5, 7, followed by ellipses. All right, so we look at the elements, understand the properties. It's in roster form, so 1, 3, so these seem to be all odd numbers, and also natural numbers, right? They are natural numbers and odd. So yes, 9 should belong. So the element following the number 7 should be a 9, correct? So this is a true statement. This is a true statement. Why is it true? Because the set is a set of natural numbers and X is odd. The elements are all odd. Therefore, 9 being in the set of natural numbers and also being an odd value makes the statement true. All right? And then finally, we have 2 belongs to the set of X such that X is an odd natural number. This is also false because, yes, 2 does belong to the set of natural numbers, but 2 is not an odd value. 2 is an even value, right? Therefore, it's false. So false because 2 is not an odd number. Even though it's a natural number, it is not an odd number. It should meet both the conditions that define the set. All right, in this case, it only meets one condition, that it is a natural number, but it doesn't meet the condition that it should be an odd number. All right? Let's look at the next set of questions, which is to determine whether the pair of sets given below are equal, equivalent, both, or neither. All right? But before that, we need to remind ourselves what we mean by equal and equivalent. All right? Equal means the sets, two or more sets have the exact same elements. That's what makes sets equal. All right? Exact same elements. They may not be in the same order, but they have to have exactly the same values for the elements. Equivalent means they have the same number of elements. So if one has 3 elements in it, they may not be the exact same elements, but as long as they have the same number of elements, that then they are equivalent sets. All right? So if you recall, we discussed something called cardinality. All right? Cardinality refers to the number of elements in a set. Number of elements. So these are some terminologies that we had learned when discussing the concepts in set theory. All right? So 2 sets are equal if they have exactly the same elements, though they may not have been arranged in the same order, but as long as the element values are all the same, they are equal. Equivalent refers to sets that have the same number of elements, and cardinality refers to the number of elements. All right, so cardinality is a numerical value. Correct? So let's look at these pairs of sets. The first one is a set with elements lion, tiger, and monkey. And B is a set which has tiger, monkey, and lion. All right? So let's look at the values of values, even though they are not arranged or ordered the same way, but there's a lion in A, there's a lion in B, there's a tiger in A, there's a tiger in B, there's a monkey in A, there's a monkey in B. So that's what makes this set equal. They have exactly the same elements, but the cardinality, all right, the cardinality of each, the number of elements in A is 3, all right, 3 elements in both. And that's what makes it equivalent. 3 elements in both sets. All right, so it's not only equal, it's also equivalent. So the answer should be both, right? So let's mark it as both. All right, let's go on to the next one. The next one says A, set A has the elements purple, green, and yellow, and set B has Q, R, S. So the elements are completely different, right? None of the elements are the same in the set. However, so they are not definitely equal, all right? Since the element values are completely different, they are not equal. However, they are equivalent because set A's cardinality is a 3, correct? The number of elements in set A is a 3, and in set B is a 3 as well. So that's what makes it equivalent. They are equivalent set. What about the next one, where set A has elements grapes, apples, oranges, and set B has grapes, peaches, apples, oranges? So first of all, there are some elements that are common in both A and B. However, for two sets to be equal, they have to have the exact same elements. Now, B has an extra element called peach, which is not in A, correct? Therefore, it's not equal sets. Not equal. They are not equal because their elements all have to be exactly the same. How about the cardinality? As far as cardinality is concerned, A has 3 elements, B has 4 elements, correct? So they don't have the same cardinality, therefore it's not equivalent either. Not equivalent, so the answer is going to be neither, right? It's neither equal nor equivalent. And then finally we have A is the set of states. So A is a set of all the states of the countries. We should have specified of the US. Let's add that. Is the set of the states of the USA. And B is the set of state capitals of the US. All right. So given that, the states, the names of the states and the names of the state capitals would be different, correct? So they wouldn't be equal sets. However, every state has a state capital. Therefore, these would be equivalent. The number of states would be the same as the number of state capitals and vice versa. However, the individual names of the states are not the same as the names of the state capitals. So the answer to this is they are equivalent but not equal. All right?